We'll now look at some other continuous distributions. We have discussed the normal distribution, its properties, how to estimate it, and how to use it in our day-to-day lives. Now we are now going to discuss certain additional continuous distributions, principally the gamma distribution, the beta distribution, the exponential distribution, the log normal distribution, the Weibull distribution. There are many. So we just to give you a sample on how these distributions are estimated using R. Unlike estimating these distributions in Excel, estimating them in R is fairly straightforward, and from an application point of view, it is very, very useful. But one has to work quite extensively with these distributions, what I taught you earlier, before you can really utilize it in a very meaningful manner in your study. So let us now open R. We've opened R. And then as usual, we'll first set the workspace, and now I might set my workspace as videos in Dropbox in videos. So I run it. It is run. And now I am now going to create a database. You know that the distributions that we are going to discuss are the gamma, the beta, the exponential, the log normal, and the Weibull. So let me just the gamma, beta, log normal, Weibull, exponential, and Weibull. So these are the distributions that we are going to look at. And see how we are going to estimate it using it. And you'll come to know it's fairly easy and follows the same pattern as we did it for the normal distribution. So like we always start. Let us start with the normal distribution. Sorry, gamma distribution. The gamma distribution is not a symmetric distribution, unlike the normal distribution. And the gamma distribution has two parameters, which we shall discuss. And just to recollect, so we have a probability density function, which helps us to generate the values of the distribution and the probabilities thereof. So you can calculate the mean and the standard deviation. The mean of the distribution is r divided by lambda. R and lambda are the parameters, and the variance is r by lambda squared. So once you know the parameters, estimating the mean and standard deviation is a fairly easy task. So the gamma distribution, the shape of the distribution varies with the values of the parameters. If r is 1 and 1, the gamma distribution has an exponential decline. When r is greater than lambda, then it has a little skewed distribution. So when the difference narrows down, when the r is greater than the lambda, then it's a little skewed. As it comes closer, then the distribution gets a little more normally distributed. Right? So these are the properties. So the important thing. Now, in any for any distribution, there are only two parameters. And understanding of those two parameters are very critical, because unless you have the parameters, you cannot estimate the distribution. You cannot estimate the distribution. So you need to find out what those parameters are before you can generate the distribution. And the parameters are which is thrown up by the data itself. For instance, the two parameters of a gamma distribution are alpha and r. That is alpha and r. The two parameters of the gamma distribution are alpha and r. And you can see how the alpha is calculated. Alpha is calculated as mean of the variable divided by the variance of the variable. So that's alpha. And the r is calculated as mean of the variable divided by the standard deviation, the whole squared. Right? So I've got the two parameters. Of course, mean and standard deviation, you know how to calculate. I will not get into that. So now we know the parameters, and once I know the parameters, I can now generate the gamma distribution. So I'll call the distribution gamma, as I did earlier. I'll call it gamma, and then you may recall when I generated a normal distribution, I got it by using the word R norm. So taking an analogy from there, to generate a gamma distribution, it is R gamma. Open a bracket. And it tells you how many values do you want, and you just keep the same number, 10,000. And the values of the parameters, the value of alpha and the value of r. For the time being, let us take the values from here. I'll take 7.5 is r and lambda is 3.6. So it will be r and lambda. So 7.5 and 3.75. 7.5 r. So r is 7.5. So lambda is 3.75. So I will first give alpha. Five. 3.75. And gamma is the alpha is 3.75 and r is 7.5. So it asks you in that order. It asks you the shape and so it is 7.5. So you've generated a gamma distribution using the command r gamma. So 10,000 observations will be generated randomly. The shape parameter is 3.75 and the rate parameter is 7.5. These are the two parameters of the gamma distribution. So I've generated the gamma distribution, and now I will plot it with the command ist. The gamma distribution variable is called gamma itself, so that we don't confuse it with the other distributions, and we get a distribution which is slightly skewed to the left. So here you got the values, and here you got the number of times, because we got 10,000 observations. There are 1,000 odd values in the lowest class interval, and so on and so forth. So now we want to see the probabilities rather than the numbers, frequencies. You can just say prob equal to true. Prob is equal to true. Sorry, not there. It doesn't come there. It comes in the histogram, not here. It comes here. Okay. So you get the probabilities. What are the probabilities that these will be the values? Then we can get the density, which is a smooth curve, with the command plot. Plot, forgot. Density, open a bracket, and close the bracket. So you get a smooth curve. You can see it's skewed to the right, and you can later. Now we'll also see the skewness in the kurtosis, and for that you may recall I'll first have to invoke the library called agricole. You don't have to remember it. You can always get help as and when you need it from the net or from R itself. Skewness, and you'll ask for gamma. Right? So you get a skewness of 1. Therefore, it is not a normal distribution. Skewness should be 0. And let us also look at kurtosis. Is 1.8. So it's not a normal distribution, as we already know, just a kind of confirmation as to what the distribution would be. Now there are certain additional things that you could do, right? So you can now, I'll just okay. Now I want to check whether this is a gamma distribution at all. Is it a gamma distribution at all? So in other words, I've generated the data with these parameters. Now I want to find out, supposing I give you this data gamma, is it possible for you to find out what the parameters are? That can be very easily be done. For that in R, you need a library called fit library. Fit dista plus. You need a library of fit dista plus. You need that library. Okay. So now what I'm going to do is I'm going to take this data and find out what are the parameters. So for that, so in other words, let's just highlight what I'm going to do. To estimate the parameter of the distribution, of a distribution. So to estimate the parameters of the distribution, you need this package, which you'll have to install one time, since I've already got it installed. So I'm not doing it. You have to do it if you have not already got it installed. So now I'm going to call the data fit G. That's my output file. That's my output G equal to fit test. I'm going to fit a distribution. Fit a distribution to this data called gamma. And what I want is a gamma. I want a gamma distribution. I want the distributions of the gamma distribution. Now, I've already generated it. So if I give you data, I should get back these parameters. Very, very useful command when you're working with real data. Because when you're working with real data, you do not know what the parameters are. Because whatever you generate should approximately follow the data. So now what we're going to do is, I'm now using this command fit dista plus. I'm going to fit a distribution on this data using gamma. Right? I run it. It's run. Go to the next line and I say summary. Summary. Fit G. Okay, summary fit G. So there you are. So 3.62, the actual value of 3.75, and 7.3, the value is very close. Okay, very close. And this says these are some parameters. Okay, so we do a fit. Now we will get a plot. We plot it, and we get the plot. So there is the distribution, actual data, the distribution superimposed on that. QQ plot, a QQ plot which tells you how good the distribution is, fit of the distribution is. This is the cumulative plot and just the property plot. These are all done in order to find out whether it really fits this distribution. Now, since we have generated a data set which follows this distribution, it's obvious that these fit statistics are very good. That is the QQ statistics. For it to be a good fit, all the values should lie on this 45-degree line. The cumulative should be S-shaped and the PP plot should also be a straight line. Right? So that is the properties of the gamma distribution which I generated. Now later you will be given real data and you will be able to plot it. Right? So these are all the extensions of that, so you don't have to worry. Okay. Now that you've understood the gamma distribution, let us now go and fit a beta distribution. So the same logic you could use. First generate a data, beta, fit dist. No, sorry, if I'm going to generate it, so it is beta. So it will be R beta. Open a bracket. Then you want again 10,000 observations, comma. And then this is asking you what the parameters are. Let me digress a little bit. So the gamma distribution is over. Now we move to the beta distribution. The beta distribution, an important thing that you should remember about a gamma distribution is the variable, the range of the values of a gamma distribution. It ranges from 0 to infinity. So a gamma distribution can take any values from 0 to infinity. Unfortunately, it will not take negative values. So if there are negative values in your data, gamma distribution is not the most appropriate distribution to fit. Now coming to the beta distribution. Now the beta distribution is also a skewed distribution. I mean, it's not a symmetric distribution. It's not a bell-shaped distribution. Then you may wonder what is the difference between a beta distribution and a gamma distribution. The difference is with respect to the range of the variables. So the beta distribution handles values from 0 to 1. So it's a great distribution when you're working out non-performing assets, which are all a percentage of the total loans, never more than 100%, never less than 0. So therefore, it's ideally suited to model the distribution of non-performing assets to find out what is the probability, various calculations that you use when you're using gamma beta distribution. So beta distribution also has two parameters, alpha and beta. And please see how the parameters are calculated. X bar, which is the mean, into X bar into 1 minus X bar. Since all the values are going to be less than 1, the mean will also be less than 1. So it will be X bar into 1 minus X bar, the whole thing over standard deviation squared minus 1. Gives you the parameter alpha. To get the parameter beta, it is 1 minus X bar into 1 minus X bar, the whole over S squared into 1 minus 1. So these formulas you can remember. Mean and standard deviation, of course, are calculated in the normal fashion. So the beta distribution will have values, like this, and so you will get a beta distribution. Okay, so you will have alpha and a beta. Right? So I will say get 2 and comma 4. I'll just hypothetically put 2 values. Later, with real data, we'll show you how this to be calculated. I put 2 and 4. The values seem to be okay. So the data has been generated. Right. The data has been generated and stored in a file called beta. Now I look at the histogram, and say beta, and I get the histogram, and that is also skewed, as you can see. And as I change the values of alpha and beta, now supposing I make this 1.2. And if I make this 4.8, 4.8, then the value becomes, the shape will change. So you can see then we need to find out the appropriate parameters. So it's getting a little more skewed. It's getting a little more skewed. Okay. Now, given these parameters, I want to estimate. Okay, so I'll call it fit B. B equal to fit dist. I am not invoking this library fit dist plus because it's already been invoked. I don't have to invoke it every time. Okay, so I'll say beta. Beta, comma, in quotes beta. I want the program to get me the parameters of this variable beta using a beta distribution. Right? So please see the pattern is the same. And then I do a summary. Summary, open a bracket, and I say fit B. Okay. Here are the parameters. 1.17, which is almost close to 2, and the other parameter is 4.68. 4.68, not exactly 4.8. So basically, it has been able to give you that. And then I'll say plot G. There you are. So since we have generated the data to follow a beta distribution, it will exactly fit a beta distribution. So it's just that the data happens to be a beta distributed data. So that is the beta distribution. As you can see, the beta distribution is a distribution of values. It takes values from 0 to 1. It does not take values greater than 1. If you do have values greater than 1, they have to be scaled. And you can see since the data has been generated as a perfect fit, the QQ plot gives all the points exactly on this 45-degree line. The empirical theoretic plot are bang on. There is no deviations, and therefore the data follows a beta distribution. So you need to go and find out what is a beta distribution and what are its properties and its uses. Ultimately, it is meant to find out the properties. We'll come to that a little later. Now come to the log normal. So I'm going to call it LOGN is the name of variable, and I'm going to generate it. I'll say RLOGN. Okay, log normal. Okay, since it's not showing it up, I can find out how to get a log normal by using you take a recourse to this thing method. So it'll be log norm. Sorry. So you can find the help there. It's log norm. RLNOM. No, L. There's no need of log. Lel norm. So I am going to have 10,000 observations, and I am going to have mean of 2.115 and a standard deviation of 0.113, and the generate data gets generated. Now let me look at the shape. So for the shape, I'll go for hist. So you can see the pattern. Okay, LOGN. You get the histogram. Looks fairly normal. And if the parameters change, obviously this will also change. If I make this 2 point this thing and get the distribution. So you must keep experimenting like this and try to let it become very, very skewed. Right? So I'll put it as 1.3. So you must experiment with what the distribution does. A little play with it. Okay, that's also very, very skewed. And I will say 0 point and get the log normal distribution. Okay. 5. You could really experiment and get the data. So that's a fairly good distribution. Then the next thing I always do in the same sequence is I work the plot to get the density. Because this is the data which I generated. There you are. So we get a log normal distribution that is a little, that is skewed depending on the data. Now I'm going to fit this. So what I call it, I say fit L, ln log normal. So in bracket, the data is LOGN, and this thing is sorry, that's the name of the file, sorry. So I should say fit dist, the name of the variable login, log norm, hopefully that name is correct, LNOR. That's correct. So the thing is log norm, LNOR. Okay, there's a little problem with that. I will come to that later. I will now go to the exponential distribution. So I will first generate EXP R EXP open bracket 10,000 observations. Okay, so we'll just have a look at what the exponential distribution looks like. So that's beta. A log normal distribution has, just to recollect, the log normal distribution has a density function which is very similar to the normal distribution. The only difference is the variable is log transformed. Otherwise, everything else remains the same. So obviously, for being a log transformation, the values will range, the x values will range from 0 to infinity. So it also will not take negative values. And if you do have negative values, log normal distribution to be seen has a parameter like this. And you can see the shape of the log normal distribution changes with the change in the parameter W. Okay, that's a standard deviation. So you can see the standard deviation is what makes the difference to the shape of the log normal distribution. Okay. Now we go to the exponential distribution. Exponential distribution is a distribution which declines exponentially. So the distribution functions, we have discussed it earlier. So to estimate the exponential function, since so it has only a rate, so I'll say 0.35, right? There's only one parameter that it needs. So I run it and I'll take a histogram and then I'll manipulate this value and try to get this. Yeah, so it shows a linear decline. So I'll just try different values, 1.3. So it gets a little more steeper as you decrease it and make it say 0.035. So it's changing the shape, but essentially the decline does not peak, it does not give you a peak, it just gives you a distribution. So now, given this distribution, I'm now going to estimate it. So what do? I call it fit EXP. So effective DISP, fit distribution, data is EXP, and the thing is called I'll just check if that is right. No, I do not have an exponential distribution. We'll just try. Right. So data has been distribution has been generated, and now we will look at the histogram. Histogram, yeah, it gives us the exponential distribution. We saw that earlier, right? And I can plot it. And I plot this. Yeah, this should have been summary. Summary. That gives us back the parameters. The parameter 0.035 is what we've used, right? And we shall plot the, and it gives us, this is a perfect fit, it fits the data perfectly because the data has been generated assuming the parameters of a gamma distribution, exponential distribution, and therefore it will give us, it gives you a perfect fit. As you can see, the line is straight and things like that. Okay, so now we fitted the gamma distribution, and now finally we go to the Weibull distribution. Okay, so first, as I said, Weibull equal to R Weibull, 10,000 observations, and we just have a look at what is a Weibull distribution. So we have the Weibull distribution. The Weibull distribution also is a specialized distribution. So when the values of the parameter alpha and beta, there are two parameters. The two parameters alpha and beta. So when the two parameters are 1 and 1, you get like an exponential distribution. Then if it is 3.4 and 2, you get it slightly skewed. And when it comes large, and when they're very large values of alpha and beta, then it tends to a normal distribution. So we will take the value 3.4 and 2. 3.4, 2. So generated. And we'll get a histogram. Histogram of a Weibull distribution is fairly okay. Right, and I make it 3.4 and 2. 4 and 2, okay, because it's slightly different. 4.5 and 6.5. 4.5 and 6.5. 5. Then you get a histogram. It becomes more and more normal. So that is the Weibull distribution. So the Weibull distribution has also the problem of this thing. So now let us now fit. Okay. Fit this data as Weibull. Then I have to specify what distribution I want. So just giving the distribution, it is able to. So it assumes a Weibull distribution and fits the parameters depending on the Weibull distribution. So I get a summary. Yeah. So there you are. Summary of this. Made a mistake, so not of the data, but of the estimates. So you get the summary. So the values are 1 and 0.3. Well, sorry, the estimates are 4.5 and 6.5. So it's fairly close. You get the distribution, and now we just plot it. Since we fitted a Weibull distribution, a graded data used assuming a Weibull distribution, fit is all very good, and we can see that the Weibull distribution best fits the data. So in this fashion, there are probably about 28 or 29 distributions which you can study and try to estimate it, and and try to see how it is used. And, yeah. So in the next presentation, we will discuss how these distributions are used in the practical world.